Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore the classical machine learning algorithms that formed the foundation of modern AI and understand what problems they solved, how they worked, and why they became so influential.
It's a topic that's, absolutely essential. When you look at modern AI, at all the huge language models and incredibly complex networks we have today, they really didn't just appear out of thin air.
Right.
They're all, in a very real sense, standing on the shoulders of this classical work that was being developed way back in the mid-20th century.
And that historical context gets lost so often, doesn't it? We talk about deep learning like it's this brand new thing, but the idea of a machine that can learn is, well, it's decades old.
Oh, absolutely.
I mean, Alan Turing was writing about a learning machine back in the 1950s, but it feels like Arthur Samuel's work was what really made it sort of concrete for the first time.
That's a perfect example. Samuel's checkers playing program in 1952.
Yeah.
That wasn't just a clever bit of code. It was one of the very, very first programs that could actually teach itself.
By just playing against itself.
Exactly. It got better just by playing games over and over and learning from what worked and what didn't. That was really the birth of machine learning as we actually know it.
And then just a few years later, you get Frank Rosenblatt's perceptron in 1957, which was the first real blueprint for what we now call artificial neural networks. So when we use this term classical ML, what exactly are we talking about? What's the scope?
We're generally talking about predictive models that were designed for these core data mining tasks. So things like classification, which is predicting a category.
Like spam or not spam.
Precisely. Or clustering, which is finding natural groups in your data, and also association, which is about identifying relationships. But the common thread really is that they all build a kind of mathematical map, a function that learns from a training data set.
So the mission is to give the algorithm a bunch of raw data, and it has to figure out the rules to map those inputs to some kind of predefined outcome.
That's it, exactly. And I think our mission today is to unpack some of those most vital early algorithms, the ones that are still widely used. They often power the simpler, faster models we use every day.
And we want to understand how they work without getting totally lost in the complex math, right? And see where they still have an impact, like you see in fields like, say, wireless communications.
I think we plan.
Okay, so let's start with the most straightforward approach. Supervised learning. This is where we are the teacher. We give the machine labeled data, we give it the input, and we also give it the correct output.
Right.
And the first, probably simplest model in this whole category has to be linear regression.
Linear regression is absolutely the entry point. It's how a machine learns to predict a continuous numerical outcome. The goal is, conceptually, very simple. You're just trying to estimate a dependent variable, the thing you want to predict, as a linear combination of your independent variables, the factors you're measuring.
So you're just trying to find the straight line that best summarizes the relationship between your input and your output data points.
That is the core idea. If you plot all your data, so let's say it's house size versus house price linear regression, just finds that one straight line that best fits the scattered data.
But how does it define best fit? That seems kind of crucial.
It is. It does this by defining what's called a loss function, which is just a way of measuring error. For linear regression, the standard way is to minimize the sum of the squared errors. It's a method called ordinary least squares, or OLS.
So the model looks at the distance from every single data point to the line. It squares those distances.
So positive and negative errors don't cancel each other out.
Right. And then it just keeps adjusting the line until that total sum of all those squared errors is as tiny as possible. And that gives you your best line.
That is precisely the optimization objective. And this very simple method is surprisingly powerful. In engineering, for instance, these models are vital. In wireless networks, they're used all the time to model the relationship between, say, signal quality and packet reception.
So it helps predict network performance.
Exactly. Quickly and accurately.
Okay, so linear regression is great for predicting a number, like a price or a ratio. But what about when we want to predict a category? A classification like yes or no. A straight line doesn't really work for that.
No, it doesn't. And that's where we transition to logistic regression. It's really a special, generalized version of linear regression, but it's designed specifically for predicting a binary outcome, a 1 or a 0, a yes or a no.
So instead of predicting the value itself, it's predicting the odds.
The probability, exactly. It uses the linear model to estimate the likelihood of the event happening.
But wait, a probability has to be between 0 and 1. A straight line can go from negative infinity to positive infinity. How does it squeeze that output into the right range?
Oh, that's the key trick. It uses a mathematical transformation called the sigmoid function. You might also hear it called the logistic function. It's this S-shaped curve that takes any number from the linear model and just smoothly maps it to a value between 0 and 1.
So a really high output gets mapped close to 1, a really low one gets mapped close to 0.
Precisely. And the point where that probability crosses 0.5, that usually becomes your decision boundary.
I see. So under the hood, it's still finding a linear boundary, but it's a boundary of likelihood. So I guess the biggest weakness of logistic regression comes from that same linear assumption.
It absolutely does.
Yeah.
It assumes the relationship between the variables, and critically, the decision boundary itself is linear. If your two classes are sort of swirled together, it's just not going to work well. It's trying to draw a straight line through a curve.
And I'd imagine it's sensitive to outliers, too.
Very sensitive. A few extreme data points can pull that line way off course.
But despite that, it's still a workhorse, right? Because it's so fast and easy to understand. Where would you see it in the real world?
Oh, everywhere.
Yeah.
Especially where you need a quick probability check. In wireless, it can estimate the likelihood of interference between, say, a Wi-Fi network and Zigbee devices. It's also great for things like detecting spoofing attacks, where you need a quick, lightweight, authentic or not authentic decision.
That makes sense. Okay, so that covers our linear models. Let's move away from drawing lines now and talk about algorithms that think more in terms of geometry and similarity. And the most intuitive one has to be k-nearest neighbors, or KNN.
KNN is probably the most human understandable algorithm there is. It's what we call a lazy learner. It doesn't actually build a big, complex mathematical model. It just works on the principle of, well, asking the neighbors.
Right. So if you have a new unknown data point, the algorithm just looks at the k closest data points it already knows about and takes a poll.
That's a perfect way to put it. If you set k to 5, the new point asks its 5 closest neighbors, hey, what class are you? And then it just goes with the majority vote.
So its whole identity is based on its local neighborhood.
Exactly. The whole thing hinges on a concept of similarity, which we calculate using a distance metric. Usually it's the Euclidean distance, just a straight line between 2 points. But sometimes others, like Manhattan distance, are used.
Like walking city blocks instead of flying as the crow flies.
That's the one.
You called it a lazy learner. What does that mean from a technical standpoint?
It means it's an instance-based learning algorithm. It doesn't generalize. It doesn't create a compact model or a set of rules from the training data. It literally just stores every single training example.
It memorizes everything.
Everything. The learning only happens at the moment you ask for a prediction.
Okay, let's unpack the trade-offs there. It sounds really simple to set up, but what's the cost of keeping all that data around?
Well, the initial cost is almost zero. You just load the data. But classifying a new point is incredibly expensive computationally. For every single prediction, you have to calculate its distance to every single point in your training set.
Wow.
Then you have to sort all those distances to find the k smallest ones. So the prediction time just grows and grows as your data set gets bigger.
That means your choice of k, that one number, must be absolutely critical.
It is the most sensitive dial on the whole machine. If you pick a very small k, your model becomes super sensitive to noise and outliers. You get these really jagged, complex decision boundaries.
That's high variance.
Right. But if you pick a really large k, you smooth things out and resist noise, but you also risk fuzzifying the boundary. You might start including neighbors from the wrong class in your vote.
Which would be high bias. It's that trade-off again.
It always comes back to that.
But we still see KNN used a lot, right? In things like cognitive radio networks or for indoor localization. It seems to work well when the categories are complex.
It does.
Speaking of complexity, KNN is about finding local groups. But what about an algorithm that tries to find the single best global dividing line? That brings us to support vector machines, or SVM.
Yes, SVMs are conceptually very elegant. If KNN is about consensus from peers, and SVM is about finding the widest, safest possible separation, Its whole goal is to find the optimal hyperplane.
A hyperplane being the decision boundary.
Right. And it wants to find the one that maximizes the margin.
And the margin is the empty space, the distance between that boundary and the closest data points from either class.
Exactly. And those closest data points, they have a special name. They're called the support vectors. They're the only points that actually matter. You could remove all the other data points and the decision boundary wouldn't change at all.
That makes it way more memory efficient than KNN then.
Much more. But the real magic of SVM, the reason it became so famous, is what it does when the data isn't linearly separable, when you just can't draw a straight line between the classes.
Right, when they're all mixed together. How does it handle that mess?
This is where the big innovation is. It uses something called kernel functions. A kernel function is, well, it's kind of a mathematical trick. It allows the SVM to map the original input space into a new, much higher dimensional space.
And in that higher dimension, the data that was all tangled up suddenly becomes separable.
It becomes linearly separable. You can now draw a simple, straight hyperplane between the classes in this new high-dimensional space.
So you're not actually moving the data, which would be really expensive. You're just using the kernel to calculate the relationships as if they were in that higher dimension.
That's the kernel trick. It's brilliant. And when you project that simple hyperplane back down into the original space, it looks like a complex nonlinear curve. It allows the SVM to solve incredibly complex problems.
Are there different kinds of kernels? Is it a one-size-fits-all thing?
Not at all. And that's one of the challenges. Choosing the right kernel is critical. There's a simple linear kernel. There's a polynomial kernel. But the most popular one is probably the radial basis function, or RBF kernel, which is great for really complex boundaries.
So what are the main downsides to using SVMs? They sound incredibly powerful.
They are, but they have two big drawbacks. First is scalability. Training an SVM gets very, very slow on large data sets. And second, and this is a big one, SVMs are typically black box models.
Meaning they're hard to interpret.
Extremely. They don't give you probability estimates, just a hard decision. And it's very difficult to look at the model and explain why it made a particular choice. In many fields, that's a deal breaker.
That lack of interpretability is huge. And it's a perfect transition, actually, because our next algorithm is famous for exactly the opposite reason, decision trees.
Decision trees are prized for their transparency. They're a true white box model because they directly mimic how a person might make a decision. You can just look at it like a flowchart.
So what's the basic structure of one?
It's made of 3 parts. You start at the top with a root node, which is the first feature you test. That splits into branch nodes, which are the rules or decisions. And those eventually lead to leaf nodes, which are the final outcomes, the class labels.
And the algorithm builds this tree by splitting the data over and over. What guides its choice of which feature to split on at each step?
The main goal is to increase the purity of the resulting groups. You want each split to create subsets that are as homogeneous as purely one class as possible.
How does it measure that purity?
It uses an impurity criterion. The two most common ones are the Gini index and entropy. Both are just mathematical ways of measuring the disorder or randomness in a set of labels. The algorithm picks the split that results in the biggest decrease in that impurity.
If the algorithm is so good at finding these perfect splits to make the groups pure, it seems like it would be really prone to overfitting.
That is the single biggest weakness of an individual decision tree. If you let it grow deep enough, it will perfectly memorize all the noise and quirks in your training data. It has extremely high variance.
It becomes a perfect historian of the training data, but a terrible predictor of the future.
A perfect way to put it.
And the classic solution to that problem is a technique called a random forest.
Yes, random forest is the elegant answer. Instead of building one giant, deep, overfitted tree, you build hundreds of smaller, simpler trees.
An ensemble of trees.
Exactly. And crucially, each tree is trained on a slightly different, random subset of the data. And at each split, it only considers a random subset of the features.
So you're intentionally building a lot of slightly different, weaker models, and then you combine their predictions.
Precisely. For a classification problem, the random forest takes a majority vote from all the trees. By combining the wisdom of this diverse crowd of trees, the final model becomes incredibly robust and much less prone to overfitting. It was a huge step forward.
That's a great example of how a limitation in one algorithm leads to a whole new, more powerful technique. Okay, let's switch gears to a completely different approach, one based entirely on probability, naive Bayes.
Right. Naive Bayes is a remarkably efficient classifier. It's based on Bayes' theorem, and it uses probability for decision-making. But it gets its name naive from one very big, very strong assumption it makes.
Which is?
The assumption of conditional independence.
Okay, so that means it assumes that all the input features are completely independent of each other given the class you're trying to predict?
Yes.
But that sounds, well, wildly unrealistic for most real-world problems.
It often is. In spam filtering, the word Viagra and the word discount are obviously not independent. They're very likely to appear together. But naive Bayes just ignores that relationship. It treats them as totally separate events.
If that assumption is so wrong so often, how can the algorithm possibly work well?
It's one of those funny things where being wrong is actually a source of strength. Because it makes that simplifying assumption, it needs way less training data to work well compared to something like an SVM. And more importantly, it's incredibly fast.
So that linear scalability makes it just blow past KNN or SVM on big data sets.
Absolutely. It scales beautifully. And the surprising thing is, when people have done comparisons, head-to-head on different data sets, naive Bayes often comes out on top. It just goes to show that the best algorithm really depends on the specific data you're working with.
So the simple, naive model can win just by being so efficient.
Yeah.
Spam filtering is the classic use case, right?
That's the textbook example.
Yeah.
But it's also really effective for things like anomaly detection, where speed is everything.
We've covered a lot of different models now, but the whole process of building a good one always seems to come down to balancing this thing called the bias-variance trade-off. It feels like the central dilemma.
It really is the perpetual balancing act. If a model isn't working, the reason is almost always found in this tension between bias and variance.
So let's clarify those terms for everyone. If we pick a model that's just too simple for the job, like trying to fit a really curvy data set with a straight line, what's that called?
That is high bias, and it results in underfitting. The model is just too simple. It hasn't captured the underlying pattern in the data, and it's not going to, no matter how much data you give it.
And the opposite, if we build an incredibly complex model, like a super deep decision tree that memorizes every single point.
That's high variance, which leads to overfitting. The model is too flexible. It's learned the noise, not just the signal. It looks perfect on the data it was trained on, but it falls apart as soon as it sees new data.
So the goal is to find that sweet spot in the middle. Low bias, low variance. If a model is overfitting, what are the classical strategies to sort of rein it in?
The main strategy is called regularization. It's a technique where you introduce a penalty into the model's learning process. You actively penalize the model for having its parameters, its weights, get too large, which is what happens when it overfits.
So you're almost intentionally making the model a little bit worse on the training data.
Yes.
To make it much better on new data.
That's it, exactly. You sacrifice a little training accuracy for a big gain in generalization. And there are two main types of regularization penalties, which we call L1 and L2.
Okay, let's start with the L2 penalty, which is often called ridge regression.
The L2 penalty adds a term that's based on the square of the coefficients. It basically encourages all the model's coefficients to be small and more evenly distributed. Its main advantage is that it makes the model more robust when you have collinearity.
Collinearity being when two of your input features are highly correlated with each other.
Right. Ridge regression helps stabilize the model in that situation. It shrinks the coefficients, but it almost never shrinks them all the way to zero.
Okay, and then you have the L1 penalty, or lasso regression. How is that different?
The L1 penalty is based on the absolute value of the coefficients. And because of the way the math works out, it has this really cool property called sparsity. It can, and often does, shrink the coefficients of irrelevant features all the way down to exactly zero.
Wow. So it's not just regularizing, it's actually doing automatic feature selection. It's simplifying the model by kicking out useless variables.
Exactly. It's an incredibly powerful tool. And of course, if you want the best of both worlds, there's the elastic net, which just combines both L1 and L2 penalties.
We've been focused this whole time on supervised learning, where the data has labels. Let's flip that on its head now and talk about unsupervised learning, where we just give the machine a bunch of data and say, find something interesting.
Right. Unsupervised learning is all about discovery. And the two main tasks are clustering, finding groups, and dimensionality reduction, simplifying the data. Let's start with k-means, which is the foundational clustering algorithm.
K-means is a hard clustering method. What's its basic goal?
Its goal is to partition n data points into k distinct, non-overlapping clusters. It does this by finding K central points, which we call centroids, that minimize the inertia.
Inertia just being the total distance of all points to the center of their assigned cluster.
Exactly. It wants to make the clusters as tight and compact as possible.
So how does the algorithm actually work? How does it find these optimal settings?
It uses an iterative process called Lloyd's algorithm. You start by just randomly placing K-centroids in your data. Then you repeat 2 steps over and over. First is the assignment step. Every data point gets assigned to whichever centroid is closest to it. The second step is the update step. You move each centroid to the average location of all the points that were just assigned to it. And you just repeat those 2 steps, assign an update, until the clusters stop changing.
That sounds pretty straightforward. But what are the limitations of relying just on centroids and distance?
Well, there are a few big ones. First, K-means inherently assumes that your clusters are going to be circular or spherical. If your data naturally forms long, elliptical shapes, K-means is going to chop them up incorrectly.
I see.
Second, it's really sensitive to where you randomly place those initial centroids. A bad start can lead to a bad result. And third, you have to tell it the number of clusters, K, in advance, which you often don't know.
So K-means is simple and fast, but rigid. If we need more flexibility, we have to move to soft clustering with something like a Gaussian mixture model, or GMM.
Yes, GMM is the big conceptual step up. Instead of assuming a cluster is defined by one point, the centroid, GMM assumes that all the data points were generated from a mixture of different Gaussian probability distributions.
So instead of just a center point, each cluster is defined by a whole distribution, which has a center, a spread, and a shape.
Precisely. GMM includes covariance matrices, which allows the clusters to take on these flexible elliptical shapes. It immediately solves that rigidity problem of K-means.
And to figure out the parameters of these hidden distributions, GMM uses a process called the expectation maximization, or EM algorithm.
The EM algorithm is the key. It's an iterative process, like K-means, but it's statistical. The E step, or expectation step, calculates the probability of each data point belonging to each of the Gaussian distributions.
So it's not a hard assignment anymore. A point isn't just in cluster A. It has, say, a 70% chance of belonging to cluster A and a 30% chance of belonging to cluster B.
Exactly. That's the soft assignment. Then the M step, or maximization step, recalculates the parameters of all the Gaussian distributions, their means, their covariances, to best fit those probabilistic assignments. And it just goes back and forth, E step, M step, until the model stabilizes.
That makes the leap from hard to soft clustering much clearer.
Okay, let's touch on the other major area of unsupervised learning, dimensionality reduction, basically making our data smaller. And this is such a critical task. Raw data can have hundreds, even thousands of features. Many of them are redundant or just noise. This curse of dimensionality makes things slow and can confuse the algorithms.
So we need to simplify. And the classic method for that is principal component analysis, or PCA. How does that work?
PCA uses a transformation to convert your original, possibly correlated features into a new, smaller set of linearly uncorrelated variables. We call these principal components.
And it's basically rotating the data so the new axes line up with the directions of the most information.
The most variance, yes. The first principal component is the single direction in your data that captures the most variance. The second component captures the most of the remaining variance while being mathematically orthogonal or at a right angle to the first, and so on.
So you can often capture, say, 95% of the important information in the data with just the first few components and just discard the rest as noise.
That's the idea. And it's incredibly valuable. You see PCA used in things like indoor location tracking to boil down lots of noisy sensor measurements into a few powerful features for localization.
Now, PCA just makes sure the new components are uncorrelated. There's another method, independent component analysis, or ICA, that takes it a step further, right?
It does. ICA's goal is to find components that are not just uncorrelated, but statistically independent. It's trying to separate a mixed signal into its original underlying sources.
Like the cocktail party problem, trying to isolate one person's voice from the chatter of a whole room.
That's the classic analogy for it. And you see it used in things like smart grids, to unmix jumbled signals from smart meters or to filter out jamming and interference from the signal you actually want to hear.
We've covered a lot of ground on the mechanics. Let's circle back now and talk a bit more about the historical importance of these models and why they're still so relevant. We touched on the perceptron earlier.
Right. Rosenblatt's perceptron in '57. It was the first real blueprint for a learning neuron. It's the direct ancestor of every neural network we have today.
But it hit a pretty famous wall almost immediately.
It did. The simple perceptron could only learn patterns that were linearly separable. If you couldn't draw a single straight line to divide your data, the classic example is the XOR problem. The perceptron was stuck. It couldn't solve it.
And that actually stalled neural network research for years.
It did, until the backpropagation algorithm was developed, which allowed us to train multi-layer networks that could handle those complex, nonlinear problems. The perceptron defined the problem, and later techniques finally solved it.
And we also saw how the simple high-variance decision tree led directly to the much more powerful random forest.
That ensemble idea was a huge breakthrough. It proved you could take a bunch of individually weak models and combine them into something incredibly strong and robust.
Yeah.
That idea underpins so much of modern machine learning.
So, with all the sophisticated deep learning tools we have today, why would an engineer ever reach for one of these older classical models?
Oh, for so many reasons. But it usually comes down to three things. The first is just raw speed and computational efficiency.
Right.
An algorithm like naive Bayes is just incredibly fast and lightweight. If you're working on an IoT device with a tiny battery and processor, you can't run a giant neural network. You need a classical model.
Makes sense. What's the second reason?
Interpretability. As we said with decision trees, sometimes you absolutely must be able to explain why a model made a decision. In medicine, in finance, you need that transparency. A deep neural network is a black box. A decision tree is a white box.
And the third.
They are still the best tools for the job as base learners in more complex systems. You might use a really fast naive Bayes model to filter 99% of your data and then only send the really tricky cases to a big, slow, deep learning model. They're essential building blocks.
So can you just give us a final recap of how these are used today in a complex field like wireless networks, which we've mentioned a few times?
Certainly. I mean, they're the bedrock of network management. Linear regression is used for traffic estimation, naive Bayes for fast network association. SVMs and KNN are crucial for detecting interference and classifying signal types in cognitive radio. Even outside of tech, in medicine for predicting heart disease or in industry for sorting wine quality, these seemingly simple models are at work every single day because they provide the right balance of speed, accuracy, and interpretability.
That really has been a comprehensive journey. We started with simple lines and regression, moved to geometry with KNN and SVMs, and saw how simple rules could lead to powerful ensembles like random forest.
And the whole way, we kept running into that same timeless challenge, managing the bias-variance trade-off and using tools like regularization to find that perfect balance for the problem at hand.
And we also saw the need for unsupervised learning to find hidden groups with k-means and GMM, and to simplify massive data sets with PCA and ICA. These really were the tools that let us start handling the data explosion.
And that brings me to a final thought for you to take away. The core challenges that were identified and tackled in classical ML.
Yeah.
That tension between performance and interpretability, the difficulty of finding the right model complexity, the need for good, clean data.
Mm-hmm.
These are not solved problems. They're the very same issues that continue to shape the most cutting-edge research in AI today.
Yeah.
It just highlights how truly timeless these foundations are.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.